So, welcome to lesson 3.5, which is all about networks. Now, we certainly encounter networks in socio-historical processes. We are members of social networks. There are economic networks, trade networks. There are political networks like the alliances or coalitions of nations that get together to fight wars. So understanding networks is certainly part of the toolkit of the theoretical historian. And there is a whole science of networks, and there's also a discipline of social network analysis. And in this lesson, we're going to go over some of the main ideas. Okay, here we have two networks. So a network consists of nodes joined by links between the nodes, or these are also sometimes known as vertices joined by edges between the vertices. And here we've labelled the nodes A, B, C, D and E. And on the left we've got an undirected network. So in this case, two nodes are just linked. There's no direction to it. They're either linked or not. Whereas on this side, we've got a directed network. So in this case, there is a direction to the link. So here B is linked to A, but there's no backward link from A to B. So, this means something like B loves A, or B gives tribute to A, or B buys things at A's shop, whereas A doesn't love B, or A doesn't give tribute to B, or A doesn't buy things at B's shop. So we've got directions to the links. And we can also have signed networks where we give a sign plus or minus to the links, which can mean things like friendship. A and D are friends, whereas a minus sign here means A and B are enemies. Or it might mean that they're, these aren't necessarily people, they could be countries. A is an ally of D and an enemy of B. And we can also give weights. We can have a weighted network with weights to the links. So we could, if this is whether a country exports to another country, this might represent that B exports $100 billion worth of goods to A, whereas D exports, say, $2 billion worth of goods to A. So that's something important to know, that these links we're looking at are not necessarily equal in the strength or the weight of the connection. And the way people analyse weighted networks like this is often to see how the network behaves if we take away links that are below a certain strength. So we see how different the network looks if we take away those links that are, as I say, below some threshold. Then another key idea is the degree of a node. The degree is just the number of links that the node has. So here A has degree 2, C has degree 3. And then with a directed network, we can talk about the in degree and the out degree. So here A has an in degree of 2 and 0 out degree because it's got nothing coming out of it. C has an in degree of 3. There are 3 arrows coming into C from E, B and D, and an out degree of 1. Then we can talk about a path in a network. So a path is how to get from one node to another node. So if we take the example of the directed network here, then the path from C to A would be C to E to B to A. Then that's the only path in the directed network, and it's a path, we would say, of length 3 because there are 3 links involved. In this case, that we can get from C to A by just 2 steps, either C to B, B to A, or C to D, then to D to A. And the network distance, so let's say that's the idea of the path. The network distance between 2 nodes is the shortest path between them. So in this connected network, the network distance between C and A is 3. That is the shortest way to get from C to A. Whereas in this case, you could make it in 3 steps, C to E to B to A, but the shortest path is just 2, C to B and B to A, or as we also said, you could go via D. So the network distance is the shortest path. The network distance between 2 nodes is the shortest path between them. And then the diameter of a network is the largest network distance between a pair of nodes in the network. So it's the furthest away 2 nodes can be and still be in the network. Okay, then we can talk about how connected a network is. So a network is connected if there is a path between any pair of nodes, so that from any node you can reach any other node, then the network is connected. So with undirected networks, they would typically will be connected, the networks that we would look at. It would be disconnected if we had something out here that wasn't connected into this, then it's disconnected. But usually you're only going to be considering the things that are connected, that would just be considered a separate network. Whereas with directed networks, they usually won't be connected. I mean, this one isn't connected, for example, because A cannot reach any other node because it's only got incoming links. And on the other hand, no node can reach D because D only has outgoing links, so there's no way to get to D. So usually we will find that directed networks are disconnected, but we can call a network, a directed network, weakly connected if it would be connected if we ignored the directions of the links. So if we just regarded these as undirected links, then if it would then be connected, then we can say it's weakly connected. So this one is weakly connected. If we replace the arrows with just plain old links, then this would of course be connected. So that's weakly connected. And then strongly connected is if it's connected when you take into account the directions of the links. And we can also talk about the degree of connectedness of a network, or how connected it is, in terms of how many nodes you would have to remove from the network in order to make it disconnected. So if we look here, for example, we might say, well, what happens if we take away node C? Would that make the network disconnected? Because it certainly looks like it's a very well connected node if we took it away. But actually, if we took C away, E, B, A and D would still be connected. And there's no node we can take away from this network that will leave it disconnected. But if we took away 2 nodes, so if we took away C and then took away B, then E would be disconnected from A and D. So we would need to remove 2 nodes from this connected network to make it disconnected. And so that's a measure of the resilience of the network to, attacks on it. This is something that, is of interest. For example, if you've got a military communications network and the enemy is bombing or cyber attacking your nodes, you want to know how many hits would they have to make on your network to disconnect you. And you would obviously want to design your network in a way that would make it resilient to disconnection under these attacks and removal of nodes. Now, there are two key things that people are interested in when they're looking at networks. The first is, which are the important nodes? Which nodes are most important, they want to know. And the second thing is, what clusters or subgroups exist within the network. These would be groups of nodes that are tightly connected to each other and not necessarily so well connected to the rest of the network. So those two things are the main points of interest with networks. So in terms of the most important networks, so the important nodes, people talk about the centrality of nodes. That's like the importance. How central are the nodes to the network? And there are, many different definitions, many ways of measuring this. I'll just mention three main ones, though there were, subcategories of each of these. So the first measure of centrality is just the degree of the node. The most important nodes would be the ones that have the highest degree. So in this case, C and B would be considered the most important because they both have degrees of 3, and the others only have a degree of 2. Another measure of centrality is betweenness. How much do the nodes lie between other nodes? So that's really the same as asking how many of the shortest paths in the network go through each node. So if we have a network, let's say like this, in this case, these nodes would have a high degree of betweenness, particularly this one, because all the paths to get from this part of the network to this one and vice versa must go through that node. So it has a high degree of betweenness. And indeed, if you took away either of those two nodes, you would disconnect this network into two parts. So a high degree of betweenness is a measure of the importance of the node and is also related to its importance to the resilience of the network, its importance or relevance to keeping the network connected. And then a third measure of centrality is where you consider nodes to be important based on whether they're connected to other important nodes. So, you might say, looking at this network, well, C looks pretty important here in the middle, and it's quite well connected to the others, so that's important. And then B is connected to C, so that makes B more important. But then you would say, well, because B is quite important from being connected to C, that makes C even more important. The importance of B kind of reflects on C. And then that would make B more important again, and then that would make C even more important, and so you kind of go around in a never-ending loop, and these would become infinitely important if you just did that. So what you do is you stop that process after a certain number of steps, and what you really do is, obviously in a much bigger, more complicated network than that, but you start by giving each node equal importance, and then you increase the importance of each node according to what's connected to it. And then once you've done that once, you do it again, and this time some of the nodes that were better connected will be emerging more important, and those will then make the ones they're connected to even more important. And so you now allocate the importance of each node a second time based on that, and then you can do that 3, 4, any number of times, and stop it at a certain point, and then that's the distribution of the importances or centralities of all the nodes is what you then assign to them after you've done that process. And this is the page rank algorithm of Google that measures the importance of web pages is based on that kind of idea. Pages are more important, web pages are more important if they're connected to other important web pages. And we said the other issue that people are interested in is that of clusters. So let's have a look at that. So again, as with centrality, there's a whole range of definitions of different types of clusters, and we're just going to look at some of the main ideas. So one is the idea of a clique. So a clique is a set of nodes where every node in the clique is connected to every other node in the clique. So this group of 4 nodes in this network forms a clique. But this node, although it's connected to some of them, is not part of a clique because it's not connected to these 2. So that is not a clique, but these 4 are a clique. And then we can define a core, a K core is a group of nodes such that each node in the group is connected to at least K others. So in this case here, if we include that node, we have a 2 core. Because it is connected, this one is connected to 2, at least 2 of them. Well, we're saying it's got to be connected to at least 2. Well, this one is connected to 2. This one is connected to 4, so that is certainly at least 2, and these down here are connected to 3. So we can say that for all the nodes in that set, they are all connected to at least 2. This clique is a 3 core because every node in that clique is connected to at least 3 of the others, and in fact all 3 of the others. There are only 3 others, so that's we could also call that a 3 core. And then a component is a set of connected nodes. So in this case, that whole thing is a component. Because in this undirected network, they're all connected. If we look up here, this directed network, then we would say here, well, B, C, and E form a component. They're connected. So you can get from B to C and to E, and C to E and E to B and C. But A and D are not part of a component because we've already said you can't get into this component from A and you can't get out to D from this component. So this is a component within that directed network. And we can also talk about the in component. So we can have an in component and an out component. So in the case of C here, the in component is B, D, and E. Those are the nodes from which you can get to C. and the out component are the nodes which you can reach from C, so they are E, B and A. It's the out component from C. So in component is all the nodes that can reach a certain node, and the out component is all the nodes that can be reached from a certain node. And a fairly sort of famous diagram of the World Wide Web looks like this, that there's a strongly connected core. So within this strongly connected core, every web page can be reached from every other web page just by following hyperlinks. So just with your mouse, you can click on from one page to the other, and you can get to every page within that strongly connected component. And then there's an in component, which is all the web pages from which, by following hyperlinks, you can get into the strongly connected component. And then there's an out component consisting of all the web pages that you can get to by clicking on links in the strongly connected component. Not necessarily directly, you know, some of these you may connect to a page here and then to a page here and then to a page here, but you can ultimately get to any of these pages by following links. And similarly here, this page isn't necessarily directly connected to that component, but it's connected to others that eventually are connected into that component. And then there are other components disconnected from the main part of the webs, you know, so the dark web. And in 2010, which is the latest statistics I've seen, this was about 28% of all the web pages were in the strongly connected component, and about 21% in the each of the in and out components, leaving 30% that weren't connected, or were in, you know, they were in other components. They might have been connected to other things here, but they weren't connected to this main part of the web. One thing I should have mentioned is that in mathematics, something like this, or the undirected version as well, is known as a graph. So in mathematics, the mathematics of networks is known as graph theory. That's another term that one might encounter. Okay, the next thing we're going to consider is the idea of a triad. So a triad is a set of three nodes that are all connected to each other. And one of the questions of interest is that if we've got a node that is connected to two other nodes, then is the other pair also connected? So it's like saying, you know, if A is friendly with B and also with C, are B and C friends as well? This is known as the closure of the triad. And if we look in a network, we can ask this question for every case where there are nodes that are connected to two other nodes, and say, does they, you know, is their closure, does it form the triad? And then that will, the more that closure is the case, the more that if two nodes are connected to a particular node, then they are also connected to each other. The more that that is true, the better connected the network. So counting the triads in a network is a way of measuring its connectedness. Another matter to do with triads is the idea of balance, which occurs in networks that are signed, where the links have a sign, positive or negative, friendly or not friendly. And a triad is said to be balanced if, when this node is friendly with that one and friendly with that one, then these are also friends. That would be said to be balanced. It's like saying, you know, if Fred is my friend and Jenny is my friend, then I like them to be friends with each other. If they're deadly enemies, that's not really a very, you know, happy relationship. It's not really balanced. So, but if they are friends, then, you know, that feels good and it feels balanced. Then, so this is a situation I've just described when, you know, you've got two friends, but the friends can't stand each other. This is unbalanced. So those two relationships are friendly, but that one is unfriendly. And then this, where two people, so when one person has two people who are enemies and they are friendly with each other, that is fine. So two people here are friendly, but they're both an enemy of someone else. That's like saying my friend's enemy is my enemy, which you know, makes sense. You don't want to be friendly with somebody that your friend hates, because, you know, that's an awkward situation again. So this is balanced. And then lastly, this is the case where if this is us, that person is my enemy and that person is my enemy's enemy, but it's also my enemy. Well, that is kind of unbalanced, because if you if this person is your enemy and you do harm to that person because they're your enemy, you're actually helping this person because they want harm done to them as well. So you're kind of helping this enemy by harming that one. So it's kind of self-defeating. So this is also unbalanced. And the hypothesis is that in social networks of people and their friendliness towards each other, or of countries and their relative friendliness towards each other, there's a tendency for triads to become balanced. So, if you're in this situation where this person and this person are friendly with each other, and this person is also friendly with that one, but these two can't stand each other, what tends to happen is that this friend will dump one of those, and so will keep one of the friendships and dump the other person and become unfriendly. So they will evolve towards this and become balanced. Or they might go the other way. If this person is friendly with both of these, but these two can't stand each other, that person's influence might bring them together and make them more friendly, and so they become balanced that way. But either way, triads will tend to evolve towards a balanced condition. And you can tell whether a triad is balanced or unbalanced. The quickest way is just to count the number of minus signs. If it's an odd number, 0 or 2, then it's balanced. If it's if it's an even number, 0 or 2, then it's balanced. If it's an odd number, 1 or 3, then it's unbalanced. And this idea of balanced and unbalanced triads has been used to study the evolution of the alliances between the various nations of Europe in the run-up to the First World War. So let's have a look at that. Okay, so here are the relevant nations: the Austro-Hungarian Empire, Germany, Italy, Russia, France and the UK. And the situation in the 1870s was that there was an alliance between the Austro-Hungarian Empire and Russia, Russia and Germany, and the Austro-Hungarian Empire and Germany. So these formed a balanced triad. Everyone was friends with everyone else. But these other relationships among the countries were, hostile or certainly mutually suspicious. So there were many unbalanced triads. For example, UK, Russia and France. They were in this situation of all kind of mutually enemies. And then there was a series of adjustments which I've left out in this diagram. There were various realignments and new treaties and expiry of old treaties that led by 1907 to a situation where the UK, France and Russia now had formed a friendly triad, and the Austro-Hungarian Empire, Germany and Italy were now all friendly with each other. So you had these two balanced triads like this, and all the triads in this diagram now were balanced, because if they weren't these friendly ones, then if you look at those, you'll find that there's a friendly and two unfriendly. For example, Austria-Hungary, Germany and UK. Those two are friendly, but they're both unfriendly to the UK, so that's balanced. The same applies to all the other possible triads in the diagram. So in this case, you might say that the emergence of balancing of the network was actually an ominous sign that now two clear sides were forming up that could then have a war between them. Whereas here there was no clear prospects of a war, because although there was one alliance here, there was nothing opposed to it. Okay, I'm now going to consider some different types of networks. So the first one to consider is a complete network. A complete network is one where all the nodes are connected to all the other nodes. So there's a complete network of 5 nodes. And the number of links in a complete network, if there are n nodes, is going to be a half n times n minus 1. There's n nodes, and each of them is connected to n minus 1 other nodes, because it's not connected to itself, but it's connected to everything else, so there's n minus 1 of those. And then and we're considering undirected networks here, so each we only count each link once, so although that's connected to that and that's connected to that, we'll only count one of them, so we have to divide by 2. So it's the number of links is half n to n minus 1, which is approximately half n squared, or so it's proportional to n squared. And if this is an economic network, each link represents an economic exchange, so it's something that gives economic value. So what this is suggesting is that as an economic network grows in size, its economic value that it's producing is going up as n squared, where n is the number of nodes. So that means that the economic value per person is increasing. So it's not just that economic value is increasing, it's the economic value per person, because the economic value per person will be this proportional to the number of links, n squared, divided by the number of people. So it will be proportional to n. So the economic value per person is increasing at in proportion to n. So as I say, it's n squared divided by n, so it's proportional to n. And we could also imagine that if the revenue then we're saying is revenue, so the economic value generated, economic output of a network is proportional to n squared, but the costs of a network might be just proportional to n, you know, because each one, if these are shops or something, each one has to pay rent, but its the costs are just proportional to the number. Each one has a certain cost. So revenue increases faster than costs. So as economic networks expand, again, you get an advantage from the expansion of the economic networks. Now, in reality, the number of links, you know, in societies or cities, let's say, as they increase in size, is not going to go up as n squared, because yes, in a village, a village of 100 people, that one person might know 100 other people in the village and have relationships with them, but when they move to a city of 1 million people, they're not going to have relationships with all the 1 million other people in the city. So you're not getting complete networks as you go up in size in reality of, say, cities. But what is found is that it's proportional to something like n to the 1.05 or something up to maybe 1.15. We'll discuss this when we come on to urban systems in a later module. We'll be examining this, but what you find is that the number of links goes up as something like that. So the economic value does increase. But it's not as much as n squared, you know, because when you take it, the per capita, you'll divide that by n, and the per capita is going to be then n to the 0.05 or 0.15, depending on what value you take per capita. So it is going up with the value of n, but pretty slowly, not quite, you know, proportional to n, as I suggested here. If it's the number of links and the revenue is going up as n squared, it would be n, but you know, in reality it's more like 0.05, but it's definitely still an increase. We will see that later. Another type of network is a random network. So here the idea is that you've got a set of nodes and you start linking them up at random. And let's say, you know, at first when you link them up, you're just going to get lots of pairs, but eventually you're going to do something like that and join two existing pairs. So now you've got, just by joining those two, you've now got a much more connected thing. And if your next link happens to be there or there or there, it could be, or any one of those, then you've got an even bigger connected component. And what you find in such random networks is that you get a phase transition at around n over 2 links, where n is the number of nodes. So that up to about that point, there's very little, if we put here, so here, the size of the connected component, con component, CPT, that stands for connected component. The size of the connected component up to about n over 2, it hardly increases. So that was when here, the first random links we drew only joined together pairs. And if you imagine, we got 1 million of these nodes, we'd have to go a long time. For a long time, we would just be joining one node to another just to create a pair. But eventually, when you've got to n over 2, so if it were 1 million, once you got to 500,000, by that time, almost every node is going to be part of a pair, because you need n over 2 links to make, connect pairs. If you had every node connected just in a pair with the minimum that you would need is n over 2, because each link connects 2 nodes. So if you didn't have any 3s and things, but just pairs, you would have n over 2. So that's kind of the minimum you need to get everyone at least connected in a pair. And then after that, when you start adding, you will inevitably start to connect pairs together and then bigger components together. And if you plot as n continues to increase, the number of links, that is, sorry, not n, the number of links, it goes up something like that. So once you get past n over 2, there's quite a rapid increase in the size of the connected component, and then it tails off again until when you got up to about n, you've got pretty much one completely connected component. By that time, when you get up to here, you've got almost all the nodes are linked into this connected component. There are just a few that by chance didn't get connected, are out on a limb. And also what you find here is that at this point you have a power law in the size of the connected components. So you'll have something like this, that if this is sort of the point n over 2, we have here 7, and I've got 4 links. But at this point, this is kind of the point where the power law appears, because you've got one large one, then you've got some fewer small connected components, and then more very small connected, very small connected components. So you've got a power law relationship. Well, there isn't a power law here because you've got one of each, one large, one medium, and one small. But if you had millions, you would find at this point you've got some that are really large, and then more medium-sized ones, and then lots of very small connected components of just pairs and 3s. So you'd get a power law. So if you plotted, so it did a rank size plot of the components of size against rank. So in other words, the largest connected component in the network is rank 1, and the second largest is rank 2. You would find a power law. This is a log-log plot. Whereas here, you've got a typical size. When you haven't connected very many, mostly you've just got pairs and maybe a few 3s and even fewer 4s. So there's a fairly average size. There's no really big ones. And then when you get to here, as I said, you've got one completely connected component. So the power law exists at the point of transition, the phase transition, or this is like a critical transition that we were considering in an earlier lesson on scale-free phenomena. So it's a bit like percolation, for example, where you have a grid and you fill it in. Either you can make a few dots on the grid, that's like having only a few links, or you can have most of the grid is coloured in, which is like then you have one connected component. But in between the two, where you know, at the kind of sweet spot, you get this power law appearing, where you can have some really big ones, but you've also got lots of really small ones. And so this is, you know, might be of interest, for example, if you're thinking about as through history communications between settlements improve. So at first you have a lot of small settlements scattered across the landscape, and each one's fairly self-sufficient. They're not really communicating with each other. But as transport and communications improve, some of these are going to start to connect up, and then more and more can connect up, and then at a certain point you might go through this phase transition where suddenly a huge economy starts to appear with all the different settlements all connected into this one big component that's all mutually trading with each other. So it would seem like an industrial revolution, let's say, that as you know, it looks like a sudden transition as you gradually increase the communications capabilities. You don't see a gradual change, but you see a sudden transition at a certain point. Okay, and our next type of network to consider is a scale-free network that has a power law in the node degrees. So not now in the size of the components, but in the degrees of the nodes. So you'll have some nodes that are very well connected with high degrees, connected to many other nodes, and then some nodes that are less well connected, with lower degrees, and then many nodes that are, you know, not really connected very much at all. Let's say over here as well. So the power law is when you look at the number of nodes of different sizes. The number of nodes of a given size is proportional to S, the size to some exponent, negative exponent. And these scale-free networks tend to form kind of a hub and spoke structure. So there are hubs which are very well connected, and then there are spokes going out from those hubs. So I've shown two spokes, but you know, this will be another spoke. There'll be this goes down to a kind of lower hub, which in turn has other spokes hanging off it here, and so on there, and so on. So what this means is that the way that lower nodes, I haven't actually drawn the nodes, have I? But I've just drawn the links around them, but these should all really be nodes. And nodes at the ends of each of these as well. And so on. So what this means is that if you're a typical node, you're not very well connected because it's a power law. So most nodes are, you know, very poorly connected, but they're connected nevertheless to many other nodes because they can go up through this hub and spoke structure because they are connected to some other nodes, and one of the ones they'll be connected to is a more important node that has a higher degree, is more of a hub, and then that will have links to even bigger hubs, and those will have links to even bigger hubs, you know, the top level hubs, and then you go back down. So if you're trying to get from here to here, you go up through a series of hubs and then back down through a series of hubs until you find your destination. And this is like an airline network. You know, you have regional airports, or local airports to regional airports to major international airports. And so if you're getting from Hicksville in the US to Hicksville in Australia or something, you will go up to a major international airport, and then when you get there you will go back down through little local airports till you arrive at your destination. So everything's connected, but it's through this hub and spoke structure, which shows the power law in the node degrees. And there's a suggestion then that this is kind of the most efficient way of doing it. If you're trying to get from there to there, you wouldn't want every single small airfield in the world to be connected by a direct link to every other small airfield in the world. This wouldn't be really efficient. So, but this approach of having local, regional and international hubs is a way of getting everything connected while minimizing the amount of infrastructure that you put in. And you also see this kind of a structure in maritime or port networks in the ancient Mediterranean. So I said airline networks and port networks in the ancient Mediterranean were like this as well. People have studied the ports of the ancient Mediterranean, and understanding that it is this kind of scale-free network helps you think about the archaeology of it. You can anticipate what kind of structure you're looking for, and you do find this, that there are major ports, and then between them are lesser ports, and then there are little local ports. And our next type of network is known as a small worlds network. So many people will have heard of the idea of 6 degrees of separation, based on the experiments of the psychologist Stanley Milgram in the 1960s, where he tried to see how many steps would it take for a person to make contact with a entirely random person in another city, a distant city. So he did that by giving people a package that they had to get to a named person who they didn't know, and they had to go through their own contacts. So the first person passed it to someone they thought might know, and then that to the next person, and so on. And he found supposedly that it was on average about 6 steps. So the idea then being that in this world of, well, in the United States of his day anyway, of 200 million people, it's only 6 steps from any one person to any other. And there was also an important piece of an important paper on this effect by a scientist called Granovetter, who wrote a paper called The Strength of Weak Ties, which he suggested that while most of us are well connected to the people around us, we also have a few distant acquaintances. So those are weak ties. We've got lots of strong ties. We've also got these weak ties. And it's those weak ties to other people that actually really bring the network together and make possible this 6 degrees of separation. So it's what keeps if you talk about the United States, a population of the United States as a single entity through the weak ties. And there's a model that's been developed for that, where you start with lots of nodes that are all just joined to their neighbours. And at this point here, there's quite a large distance between, you know, any node and a random other one. They're closely connected to their two neighbours, but to those over here on the other side of the network, you know, it's many steps to get round to them. But then you just draw at random some links between any pair, and suddenly by this you have massively decreased the network distance between any pair of nodes. So this one is now not directly connected to that one over there, but these also have benefited from that link, because, you know, this one is also, say, connected to that one much better than it was before. It had to go all the way around there, but now it can go do that shortcut and then come to here. And then once you add in a few more shortcuts, it doesn't take many, and you're down to that, you know, 6 degrees of separation. Almost every node is very close to every other node through these long distance ties. And, you know, that's important for thinking about how societies hold together and how economies hold together. And the last type of network that we'll consider is a tree network. So a tree network just looks like this. So there are kind of only forward links. It's like a genealogy or a hierarchy, or it's a tree because there are branches which end finally in leaves, but there's no going back on itself. There's no loops in a tree network. And this is characteristic of political hierarchies, you know, because there's a ruler who has subordinates who have other subordinates, and who have, you know, the ordinary people, the peasants at the bottom, and then there's no reverse influence. There's no control in backwards. There's no loops in the tree network. Well, maybe there is if it's a democratic system and you occasionally have elections. This kind of structure is also seen in simple societies that don't have formal political institutions, what are known as segmentary societies. So this is societies that are divided into families which belong to clans, which belong to tribes, and maybe higher level nations or super tribes. And the people in these kinds of segmentary systems say how they keep order is by or protect themselves, is that it is, they say, it is me against my brother, but me and my brother against my cousin. So, you know, I can have a dispute with my brother, but when I have a dispute with my cousin, my brother is on my side. So it's the people who are closest to you in this tree who will support you. And then if it's your, you know, your second cousin over here, then your first cousins will be joining against your second cousin over there. And then what happens in these as well is that there are cross-cutting ties. So a man from this part of the diagram marries a woman from that part, and she provides a cross-cutting tie between two branches of the tree. And there's a bit like these short circuits in the Small Worlds network. They now bring these closer together than they were, so can create mutual understanding. And also the triad thing applies, you know, because the woman who's from this branch who's married into this one, you know, has ties of loyalty and friendship with both. She tends to get the triad to become balanced so that these two become more friendly with each other. So you find that these cross-cutting ties are important in keeping the peace here, because otherwise these people would always be at each other's throats.